Welcome to my YouTube channel. I am Achu Francis Deba. Today we're going to be covering the calculations that are associated to volumetric analysis, all the calculations that are therein. But before we start with the calculations, it is pertinent we know the various formulas. We have a whole lot of formulas, and our understanding of these formulas is very key. If we remember them and how to apply them whenever we are required, that makes us excellent students. So today I'm going to give you all the formulas. We have more than 10 of them, and you have to memorize them and also know when to use them. So I will start with standardization formulas, which is the concentration. We have two kinds of concentration. We have the molar concentration and the mass concentration. But many a time, they always tell you find the concentration of, let me say, the base in mass in GDMQ. You should know that is mass concentration, or concentration of the base in mole per dm³. You should know that that is molar concentration. So, and not just that, we have other formulas that are embedded in the molar conc. So I will start by using the molar concentrations and the formulas that are associated therein and break them down to the list. So the molar concentration as our first formula, that's where we begin. So in molar concentration, we have, okay, let me start with the first formula which we can use, which is, everybody tends to know that one is simple, it's universal. So that one, A, will be CAVA over CBVB equals to NA over NB, where the CA here is concentration of acid in mole per dm³. C of VA, volume of acid in CM³ or GM³. CB is concentration, sit down, concentration of base in mole per dm³. VB is volume of base in CM³ or dm³. Na, number of moles of acid while Nb is number of moles of base. So remember I said there are a lot of formulas we use in solving volumetric analysis. So volumetric analysis calculations. So we start with that of concentration, molar concentration, which we use this as our major formula, which is our first formula. A whole lot of people are so acquainted with this one, but they tend to forget there are other formulas associated too also. So like I said earlier on, the CAV all over CBV equals to Na all over Nb. Concentration of the acid in mole per dm³, volume of acid in mole per dm³, concentration of the base in mole per dm³, volume of the base in mole per dm³, number of moles of acid, no unit, remember, numbers of moles of the base. So this is our first formula, so I call it A. I should clean this so that we can take our second formula about molar concentration. B, molar conc. This is equals to mass concentration in GDM cube over relative molecular mass in G mole. That is our second formula on molar concentration. That's BC. Molar concentration is equals to, we say, so it's amount in mole times volume in DMQ. Okay, that is our C formula on molar concentration. So we are good about molar concentration. We can move down to mass concentration. So that would be 2. Mass concentration. So the formulas that are associated with mass concentrations are 1 or A. A mass concentration in GDM cube equals to molar con in mole per GM cube times molar mass in G mole. So that's our first formula there for mass concentration. So that's A. B. Mass concentration in GDM cube, like I said, is equals to mass in gram over volume in DMQ. So for mass concentration, I think these are the two major formulas which we can use or remember. When any question is given to us about mass concentration, your mind should go quickly to these two. With the knowledge of this, you can easily understand which of them you're going to use in relation to the formula or the question that will be given to you. So that's mass concentration. The third formula we're going is amount. In mole. In mole is equals to mass in gram over relative molecular mass in G mole. 2 or B, amount in mole is equals to molar concentration in mole per GM cube times volume in DMQ. So the volume all always, most of the time they give it to you in CNQ, we convert it to DMQ. Alright? By dividing by 1000, whatever it is that is given to you. So now we move, we have amount to the mass over relative molecular mass, and amount also is molar concentration times volume. So let's go to percentage purity. Another formula which that's 4. Percentage purity. A. Percentage purity here is equals to mass concentration of pure salt over mass concentration of impure salt times 100. So that is it. We have another formula. This is A. We have another formula that is also associated. B, we say percentage purity plus percentage impurity is equal to 100. C, if this is equal to this and this is what it is, then percentage impurity becomes percentage impurity is equal to 100 minus percentage purity. So about percentage purity, we have also 3 formulas. You don't forget these ones because with the knowledge of this, you can now get this, the percentage impurity. If you remember, when you're done calculating for your percentage purity, insert it into this formula here. Purity plus impurity equals to 100. Then you can get your impurity by making impurity the subject of formula, which becomes percentage impurity equals to 100 minus percentage purity. So that is our 4th formula. Let's go to percentage of water of crystallization. That's 5 now. Water of crystallization. So in percentage of water of crystallization, we also know that we have 2 major. One is how to get our number of moles of water of crystallization, which is our X or Y or whatever the case is that will be associated with the question that will be given to you. And we also have to calculate its percentage directly. So when we talk about water of crystallization, means a particular salt is hydrated, contains water, moisture in it. So it is the amount of water contained in it that we are looking for. If, for example, it contains 5 molecules of water in it, we say, let me say, for example, if it is disodium CO3 5.5 H2O. So in this case, it contains 5 molecules of water of crystallization. So this becomes sodium triazocarbonate 4 pentahydrate. So if it is 6 hexahydrate, 7 heptahydrate, 8 octahydrate, decahydrate for 10, and so on and so forth. So this, in the question that will be given to you, this 5 will not be known. They will put it to be X. For example, you have disodium CO3.X H2O. So you will be required to find out the X. X now represents the number of moles of water of crystallization present in the given salt. Sometimes it could be 7, it could be 8, it could be 10, whatever the case is. So that is why you have to know the formula. It's very important. So like I said, for us to For us to know the number of moles of water of crystallization, which is the X, A, we have relative molecular mass of the hydrated salt over the mass concentration. Permit me to use con. We use con as abbreviation for concentration. Mass con of hydrated salt. When I mean hydrated and anhydrous, if I have this CO3.7H2O, this is hydrated. If I have sodium CO3, this is anhydrous, means it has lost all its water of crystallization. So, in the course of we or us doing that, we must certainly have to know the anhydrous nature of the salt and the hydrated. And by that, we'll be able to calculate our X effectively. So that is equals to relative molecular mass of anhydrous salt over mass con of anhydrous. So, when we start solving, you will see how this play, or that is simple. You will see how we make use of it. You understand it better, but it is pertinent for now that you should remember this formula, because if you don't remember it, I don't see how you're going to start it or survive it. You must have to remember it. It is important. So the reason why I'm giving you all of these formulas, you put them in your head. So when we start the calculations effectively, you will not be found wanting. For example, if we were dealing with any question that has to do with mass concentration, and I ask, or for example, you come across, you say, calculate the molar concentration A and B, the mass concentration. You should now know the formulas that are associated with the mass concentration. You don't need to go start flipping the pages of your books to find out. You know all the formulas associated. Therefore, with the variables that will be given to you, you will know the exact one that will be used. It is important you know that. So that is that about A. So the B, how do we get the percentage? The percentage now is, remember, we are always having, for example, X water. I gave you the formula which I said before, disodium triiodocarbonate for XHO. This is for water. So when you're done calculating and you have known what X is, that X times the molecule of water, which is always 18. Water is 18. The relative molecular mass of oxygen is 16 times 2 of hydrogen give you 18. So 18 times X. So for you to be able to calculate the percentage of water of crystallization, become the mass of this X18, which is, I call it X water, all over the total compound, hydrated compound, which is this and this. So I'll call it total compound in my own language. Total compound times 100. So in that sense, when you do that, you'll be able to estimate the exact percentage of water of crystallization. You know, what was the percentage? Was it 20% of water that was in it, or 30% in terms of percentage? Do you understand? So, do we have more? Yes, we still have another formula. It's relative molecular mass. Remember, I told you earlier on that we have GDM cube, which is the mass concentration, is equal to molar con times molar mass, or relative molecular mass. So molar mass now would be equals to what? You divide both sides by this. So we have mass concentration in GDM cube over molar concentration. Molar concentration in mole per dm cube. That is 1. So let me call that 6A. B. We also have somewhere in mole concept where we say amount equals to mass in gram over relative molecular mass. So our relative molecular mass from change of subject can be A relative molecular mass is equals to mass. So molecular mass is equals to mass over amount. So we have the next one, which is relative molecular mass is equals to mass over amount. Amount in mole, mass in gram. So these are the 6 basic formulas that are required. When we get to redox titration, we are still going to use the redox to solve practically almost everything which we are dealing with here, water crystallization, percentage purity. But before we get into redox fully, I have to show you how to balance redox equation. It's very important. When you know how to balance it, then you can proceed with the calculation. Without the knowledge of how it is being balanced, I don't see how you get around it. So this will be all for now. Thank you.